Our next speaker for this session is Professor Rahul Pandit. He's going to talk about the 3D axisymmetric Euler equation, a pseudospectral investigation of a potential finite-time singularity and thermalization. Over to you, Professor Pandit. Again, yes, please. Yeah.
I would like to begin by thanking the organizers not only for inviting me for this wonderful meeting to share some of our work with you, but also for keeping this meeting going since 2004. Okay, I mean, hats off to them. They've done a wonderful job, all of them, many of whom are in the front row, and we look forward to many more such wonderful meetings. I chose this topic because it straddles nonlinear dynamics, albeit of an extended dynamical system, and some statistical physics. And since this meeting is a satellite meeting of StatPhys, I thought this would be a reasonable thing to talk about. So the title is a mouthful, as you have learnt already. I will explain everything in the title as we go along. These are the people who've done the hard work. Actually, Sai Shweta has done most of the hard work. Puneet started on this when he was an undergraduate, and he's about to get his PhD from the Max Planck Institute in Göttingen from the group of Hemminghaus. Okay, so history, motivation, models, methods, and so on. All of this will probably mean nothing to most of you, so I will explain this as I go along. All of you must know the equations of motion for a fluid, in particular an ideal fluid which has no viscosity. They were written down 268 years ago by Euler in this very famous paper which appeared in French. There are English translations available. And even though it's been around for 268 years, we do not know several things that those who are mathematically inclined would like to know. It is known in 2 dimensions that solutions of the 2-dimensional incompressible Euler equations with analytic initial data do not exhibit a singularity in finite time. However, it is not known if any of the solutions of the 3D Euler or its viscous descendant, the 3D Navier-Stokes equation, which incidentally is 200 years old now, can develop a singularity in finite time with arbitrary analytic initial data. And the answers to these grand challenge finite-time singularity problems have also important implications for turbulence, because even if we restrict ourselves to the 3D Euler, it can have dissipative solutions as first conjectured by Onsager, and then there's a whole lot of studies of it. If the velocity field is not sufficiently regular, then you can get dissipation, which is, okay, let me not dwell on that today. Now, explorations of the finite-time singularity problem often use direct numerical simulations to get some intuition for what sorts of initial conditions might lead to finite-time singularities. And this search, although carried out by very, very distinguished and experts in this field, have not yielded unambiguous results for or against a finite-time singularity for the 3D Euler equation. Up to about 2005, the situation was summarized in this very nice article by John Gibbon. But it's still unsolved, this problem. Now, we will not look at the full 3D Euler problem in this talk. We will look at the 3D axisymmetric Euler. By the way, if you solve the 3D Navier-Stokes problem, you will get $1 million. It's one of the clay math problems. But we will look at this problem, which might look peculiar to begin with, the 3D axisymmetric incompressible Euler, But it has a history, and I think this important paper first brought to the attention of the world that in this particular 3D axisymmetric Euler, there is a potentially singular solution. This is by Luo and Howe, excuse me. And they used a high-order finite difference method, suitably Galerkin truncated, and so on. And given the importance of this problem, it really behooves us to study this solution by a completely different numerical method, because, otherwise, in your heart of hearts, you might say, oh, probably it's an artifact of finite difference, and you go this or that. And for many years, we had discussions of this with various people, including Frisch. And then we thought we should do it by some pseudospectral method. They did it by a Cauchy-Lagrange method, which I will mention towards the end of my talk. We did it by a pseudospectral method. But some more background before I get into the actual solution. Here is a celebrated paper by Beal, Kato, and Maida, which tells you how to check numerically for a finite-time singularity. And it is based on, okay, I'll give you the exact thing later. This relies on the integral of the so-called L infinity norm, or the supremum of the vorticity. You don't have to look at any other gradients. So we developed a pseudospectral. Now, pseudospectral, normally when we do everything with periodic boundary conditions, we do Fourier in every direction. But now we have an axisymmetric Euler. It is a cylinder with periodic boundary conditions in Z, but a boundary at r equal to 1. Therefore, you cannot use naive Fourier. You have to use a Fourier-Chebyshev scheme, which we developed. And then there is a method which is different from the Beal-Kato-Maida method, which looks for singularities in complex space and uses something called an analyticity-strip method, which I will describe, which goes back to Sulem, and L. Frisch, who did it first for the Burger's equation. Okay. Now for the statistical physics background. There is a long history of the study of thermalization. It goes back to Hopf, who looked at it in the context of the Burger's equation, and to T.D. Lee, who looked at it in the context of the Euler equation. They said that if you take any spectrally truncated version of these equations, and I remind you, on any computer, it's always truncated. You do pseudospectral, you'll keep a finite number of modes. Now, this is Euler, and you can even show that the truncated system also conserves the energy. So for all the statistical physicists in the audience, it's microcanonical evolution. Eventually, you get equipartition, and when you put in all the factors in 3 dimensions, the energy spectrum should go as k squared, in 2 dimensions as k, and in flat in 1 dimension. So this is quite different from the celebrated k to the minus 5/3 Kolmogorov spectrum. And people who knew both all these things wondered what does one have to do with the other, until this very nice paper by these 4 people from the group of Marc Brachet in the École Normale in Paris. This shows you a fairly high resolution simulation of the Euler equation in 3D. And you see that at large, so this is log-log plot. At large k, you see these lines coming up. So what's changing along these lines is time. And you see this is the development of the k-squared part of the spectrum that Lee and Hopf had told us about. Now, these high k modes thermalize fast. The low k modes thermalize slowly, as we would expect on general grounds. And while these high k modes are thermalizing, they act as sort of like an effective heat bath, which gives the rest of the low k modes a sort of viscosity, if you like. And if you look at this region, you can fit a defensible minus 5/3. So, but slowly the k squared consumes the minus 5/3 part of the spectrum. Okay, so this is a very nice study, the first study of thermalization in these systems. So here's the set of equations we will look at. This is the 3D incompressible Euler written in vorticity and stream function form. Don't worry about the details. So psi is this vector-valued stream function, which is related to the vorticity by that equation. Okay, now I'm going to do something you can assign for homework if you teach mathematical physics. Write it all out in cylindrical coordinates, and that's what I have done here, or rather my student has done. And then you divide out the r to, because otherwise there's some subtlety at r equal to 0. And believe me, when you write all that down, you get this set of equations. And this is the Poisson equation now, and these are all that you have to solve. Okay, we will look at analytic initial data. So just forget about the details there. And we will use the initial condition made famous by Luo and Howe. So there's a sign, and there is some thing which is defined between 0 and 1 for r, so that's radially bounded. 0 to L in Z, but we use periodic boundary conditions. Okay, so the Fourier-Chebyshev that we will do, any function of r and z, we will expand e to the I k z and z, and Chebyshev polynomials of the first kind of order m, etc. If you look at your simulation domain, that's the periodic direction, and here you can see, because of Chebyshev, the points are scrunched up near r equal to 0 and r equal to 1. So this was the paper in which we presented our results, and I will just give you a quick overview of those results in the remaining part of this talk. Now, why might you expect such a singularity? This was spelled out nicely in this paper by these mathematicians. So if you look at the initial condition, this z is the periodic direction. The velocity here will go this way, velocity here will go this way. There is a symmetry plane, which is x, y, z, x, y minus z. And when you put it all together, eventually you will see when I present the simulations that there'll be a secondary flow, which looks like this. And there is a sort of stagnation point here where some flow is coming from the top and going from the bottom, and that is the possible finite time singularity. Okay, we'll keep track of the energy and helicity to keep track of how well we are doing with the numerics, because those should be conserved. And here is the Biel-Kato-Maida theorem. It tells us that the smooth solution of Euler blows up at some time capital T, if and only if the integral of the L infinity norm of omega integrated over time hits infinity. If it doesn't, then you have no blow up, otherwise you do. There's another simpler model which I will not motivate completely, which is sort of a toy one-dimensional PDE written in terms of U and V and omega, and V is related to omega via Hilbert transform. This is a sort of model that mathematicians like to play with. The Hilbert transform is a sort of 1D cartoon for the Biot-Savart law, but forget about it. In some cases, at least for this part of the talk, you forget about it. There is a way of motivating this 1D model from this axisymmetric Euler. Now, we did pseudospectral investigations, and we also found some things which are now called tygers. These were first found by, I'll show you the paper in a minute, by Samriddhi Shankar Rai and Uriel Frisch, Takeshi Matsumoto, and Sergei Nazarenko. Let me show you what they are. If you take a solution of the Burger's equation and you plot u versus x, so this is 0 to 2 pi, that's the beginning of the shock. But just before the shock forms, you get this oscillatory structure here. And this they call tygers. Now, you could say, is it just a Gibbs phenomenon? And they said, no, it's not Gibbs, because Gibbs would have shown up here near the discontinuities. But if you go back and look at the old literature, there is a whole history of finding such oscillatory structures, and people spend a lot of time trying to come up with numerical schemes that will damp out such oscillatory structures, which I will not get into today. They discussed it, and we are doing much more, which I will tell you privately if you're interested. So these tygers, and they noted that these are the way that this truncated version of the PDE will start going towards thermalization. Okay? So we will see much of this as we go along. Now, one word about this analyticity-strip method. So the claim is that if there is a singularity, and we look at it in the complexified space like here, then this singularity tries to come towards the real axis, and if and when it hits the real axis, you have a finite time singularity. And if there is such a singularity, then the Fourier transform of the velocity will scale, just look at the dominant part, e to the minus k delta. Okay? And delta is a length, obviously, and delta is the distance in the complex plane of the singularity from the real axis. So you can use this numerically to track whether the singularity is going to hit the real axis in finite time. Okay? Now, whenever you do such things, and it's right before lunch, so I will not worry you with the details. Okay, you better check your numerics very carefully. And at least my student has done that. Along the way, you have to solve a Poisson equation. A Poisson equation is completely trivial if you have completely periodic boundary conditions. However, once you have this radially bounded thing, there are many schemes, and she has compared two schemes, Tau and Shen-Galerkin, the Tau method and the Shen-Galerkin-Poisson method. And in short, we are doing the best that anyone can in these calculations, and our solvers are working well. We also check that our code reproduces well-known exact analytical solutions for the static case, which are solutions for the axisymmetric Euler due to this group. Okay. Now, to show you whether we have a singularity or not. So this is analyzing it the Biel-Kato-Maida way. So it's conventional to take 2 logs of omega infinity, plot it versus time, and if there is you identify the time of potential singularity. This line is the Luo line. Okay. In our simulation, because it's Galerkin truncated, you get tygers. Okay. Nevertheless, given the analyticity-strip method that we use, we can identify the time of singularity. Okay, so when you just have a periodic box, the energy spectrum is simple; it's just mod UK squared and so on. But here you have to be careful because it is Fourier-Chebyshev, and these are the appropriate spectra. Let me show you some plots of these spectra. So this is, K is in Z. This is at R equal to 1. Initially, the spectrum is like this. Then it starts rising, and then it rises here. So this is thermalization for this case, all right? This looks broad here because there's some oscillation here, which is an even-odd oscillation having to do with the symmetry of the initial condition. You see, this is a semi-log plot, so from these slopes, you can extract that delta which I talked about. So that will tell you about the distance of the singularity in the complex plane. Over here, I have shown you the other type of spectrum, which is in the z equal to 0 plane, but plotted versus the Chebyshev index. And there also you see the same type of thermalization that occurs in the other direction. All right, this is comparison with other models. I can show you one movie if you like. So this is, the stuff is near k equal to 0 and then it builds up. And that's how the thermalization is taking place. I don't know whether this is very informative or not, but basically all I'm saying is initially on a semi-log plot, something is falling exponentially and then suddenly it thermalizes, at which stage you're not really solving the partial differential equation, but you're solving the Galerkin truncated equation, which is a microcanonical evolution, and that's what you're getting. So here is a nicer plot showing the tigers. I don't think anybody had seen such beautiful tiger-like structures in any 3D calculation until our work. So this is one of the components U versus Z, which is the vertical direction, which is periodic. And you can see this oscillatory structure showing up, again zoomed in and so on. And you can identify the time at which the tigers are born, after which you really shouldn't be looking at this as a PDE solver. The same thing happens in that 1D Hilbert transform model, which I just mentioned but did not define because of lack of time. And then, from these plots, you can use the generalized analyticity-strip method, which I mentioned, for this Fourier-Chebyshev case, and plot it versus time. And you can see that it goes to 0, and we can do various fits. So, for example, this is log of the even-type oscillations. It's going to 0 as the power law, and here also it's going to 0 as a power law, both in the Chebyshev direction and in the this direction. So the good news is that our calculations are in consonance with those of Howe and Luo. We, as far as we can tell, there is a finite time singularity, and this is a completely independent method. So I can give you more details of the analysis, but let me not inflict so much technical stuff before lunch. So there were some other studies also. This is by Dwight Barclay on he also did Fourier-Chebyshev, but he wasn't looking at finding the singularity. He just assumed that Howe and Luo are right. And here's a very nice, for those who are interested, on a physical understanding of how such a singularity might occur. Because you must realize it's incompressible Euler. Even though some of the profiles become quite sharp, they look almost like Berger's shocks. But strictly speaking, we can't have a shock. It's an incompressible system. So there is still some things to understand there. And here is the Cauchy-Lagrange method, which was done by Hertel, Bess, and Frisch. They also found agreement with the singularity. Now, there are other things which let me not dwell on now, but I can tell you about one extension that we have done. Yeah, I'll be done in 2 minutes, which is for the ideal MHT equations. Okay, so the same thing works. To make a long story short, we have a potential for a finite time singularity in ideal MHT also. So here are the conclusions. We've developed this Fourier-Chebyshev method, and we will extend it to ideal MHT soon. And this other 1D cartoon model, which the Hilbert transform also shows this finite time singularity. So even though tigers are born, even though there is thermalization with any finite resolution, we can still use the analyticity-strip method to uncover this finite time singularity. And now the ball is in the court of real mathematicians who can try to prove if this thing really exists at a level which is of mathematical proof. I'm sure groups are working on it, but I do not know whether there's a final word on that. With that, I thank all of you for your attention. Thank you.